Good day. Today we will be discussing methods of expressing concentration. This lesson discusses the use of various expressions of concentration, in particular, percent and ratio strengths, and relevant expressions in pharmaceutical compounding and in preparation of pharmaceutical solutions. Also included in this learning module is a brief introduction to common expressions of concentration used in the laboratory, such as molarity, molality, and normality. At the end of this unit, the student will be able to first define the expressions percent weight in volume, percent volume in volume, and percent weight in weight. Second, define the expression ratio strength. Third, convert percent strength to ratio strength and ratio strength to percent strength. Calculate the percent strength and ratio strength of a pharmaceutical preparation. Fifth, apply percent strength and ratio strength to calculate the quantity of an ingredient present in a pharmaceutical preparation. Apply percent strength and ratio strength to calculate the quantity of an ingredient to use in compounding a pharmaceutical preparation. Seventh, define molarity, molality, and normality. And finally, apply calculations of molarity, molality, and normality to preparations of pharmaceutical solutions. In preparing solutions, remember that a suitable volumetric flask is required to be used if you need to prepare a solution to a certain volume. In order for you to prepare a solution, an amount of the solute is weighed out on an analytical balance, and then a portion of the solvent is added to the volumetric flask. Now, before you fill the volumetric flask with the solvent, make sure that you've allowed the solute to be dissolved first in that amount of the solvent. The mixture is swirled until all of the solute is dissolved. Normally, we place only half the required volume, that is about 250 ml, before we completely fill the volumetric flask. The first volume that is placed is used to initially dissolve all of the substance or the solute in the solvent. Then, additional solvent is added up to the mark on the volumetric flask. Remember that the volumetric flask is calibrated only to a singular volume. So if the volumetric flask states that the mark means you have already reached 500 milliliters, you need to add the solvent up to that mark. The volume of the solution, therefore, is 500 milliliters. Another important thing to note here is that the volume of the liquid that you place as a solvent is not necessarily the same as the volume of the solution that needs to be prepared. The solid may itself occupy a certain volume. So, the volume of the solvent that you use to prepare a solution is not necessarily the same as the volume of the solution. Now, when it comes to percent strength and related expressions, we have the following terminologies. We have percent weight in volume or percent weight in volume. We also have percent volume in volume or percent by volume. And we also have percent weight in weight or percent by weight. Now, by convention, solutions such as ophthalmic, nasal, otic, topical, or large volume parenterals and lotions are expressed in terms of percent weight in volume. Aromatic waters, topical solutions, and emulsions whose solutes are liquid are typically expressed in terms of percent volume in volume. Lastly, ointments, creams, and gels, which are solid or semi solid pharmaceutical products whose amount is typically expressed in weight, and the solute is also a solid or semi solid. Their concentrations are typically expressed as percent weight in weight. Now, what do we mean by percent or percentage strength? Remember that the terminology percent means per hundred or in a hundred or by a hundred. So when we say percent weight in weight or percent weight per weight, it only means that we have an amount of a solute in grams per 100 grams of the solution or the mixture. Another formula that we may use for percent weight in weight is the weight of the solute divided by any weight of the solution or mixture times 100. Now, in most of my calculations, I normally use the symbol percent. But remember, this percent is a unit. It is not used in any calculation. When you plug in your calculator 100%, well, including the percentage sign, then it will be equal to 1. Okay? So when you see the percentage in my calculations, I only use it as a unit, which will not be used in any calculation. So I use that as a unit so that when I cancel the units in this ratio, what will be left is the percentage. Thus, I will know that what I am computing is a percentage. Now, percent weight in volume or percent weight per volume is basically the grams or the weight of the solute per 100 milliliters of the solution, or in terms of semi-solid substances, the mixture. For example, in lotions. It also means it's the weight of the solute per milliliters of the solution or mixture times 100%. Now, weight, the percent volume in volume is basically the number of milliliters of the solute being liquid in nature divided by 100 milliliters of the solution. This is the same as the number of milliliters or the volume of the solute divided by the milliliters of the solution or the mixture times 100%. Again, the percentages here are only used as symbols or units. Now, some related expressions may be used in pharmaceutical preparations. For example, you may see related expressions of concentration such as grams per milliliters, milligrams per milliliter, or milligram percent. Now, milligram percent means it's the number of milligrams of the solute per 100 milliliters of a solution. Now, for certain solutions, which are very dilute, we often use ratio strengths. Ratio strengths are basically strengths which are expressed as ratios such as 1 is to 10, 1 is to 25, or 1 is to 1,000. Now remember that the first number refers to the amount of the solute, while the second number refers to the amount of the solution or the mixture. Now, just like in percent strength, ratio strengths can be expressed as weight in weight, volume in volume, or weight in volume. What does it mean? If the ratio strength is expressed as weight in weight, then it means that a 1 is to 10 solution is basically containing 1 gram of the solute per 10 grams of the solution or the mixture. If, for example, the ratio strength is given as volume in volume, then it means the solution contains 1 milliliter of the solute for every 25 milliliters of the solution or the mixture. Now, if the ratio strength 1 is to 1,000 is expressed in terms of weight in volume, then it means that the solution or the mixture contains 1 gram of the solute per 1,000 milliliters of the solution. Now, we can convert ratio strength to percent strength. For example, 1 is to 10 is the same as 1 divided by 10. Let us suppose 1 is to 10 is a ratio strength that is given as weight in weight. So this means there is 1 gram of the solute for every 10 grams of the solution. So if we were to convert this to percent strength, we will simply perform ratio and proportion like this. To determine the equivalent percent strength that is also in weight, we will use this ratio and proportion. So the X is basically the percent weight in weight, and that is equal to 1 gram of the solute divided by 10 grams of the solution or the mixture times 100 grams equals 1 gram divided by 10 is zero point 0.1 times 100. So this will be equal to 10 grams, 10 grams. So 10 grams of solute are present in 100 grams of the solution. So the numerical value that is 10 is our percent weight per weight. So that's equal to 10%. Now let's say we have 1 is to 25. That is a ratio strength in volume in terms of volume in volume. So 1 milliliter of the solute is contained in 25 milliliters of the solution. So to be able to get the percentage volume in volume equivalent of this one, we can use the formula or we can use the um, ratio and proportion method. So we will simply need to know what is the amount of the solute, also in milliliters, that will be contained in 100 milliliters of the solution. So y is equal to 100 divided by 25, and that is equal to 4. So we have 4 milliliters of the solute present in 100 milliliters of the solution. So the percent volume in volume is equal to 4 ml per 100 ml times 100% is equal to 4%. Now, if the ratio strength is 1 is to 1000 and it is in terms of weight and volume, so we have 1 gram of the solute in every 1000 milliliters of the solvent. So again, we can use ratio and proportion here. So we have Z will be equal to zero point 0.1. And what is this zero point 0.1? This is the weight in grams of the solute contained in 100 milliliters of the solution. So we can determine the percent weight in volume as zero point 0.1 gram per 100 times 100. And the answer will be 0.1%. Now notice, just like before, the x value that you will get in the ratio in proportion will give you the same numerical value as any type of percentage. So over here, the x is equal to 10 or 10 grams, and the percent weight in weight is 10%. Over here, the volume of the solute is 4 milliliters, and the percentage in by volume is equal to 4%. Over here, the weight of the solute in 1000 milliliters of the solvent is equal to zero point 0.1 gram, and the percentage weight in volume is equal to 0.1%. Now, even more dilute solutions, such as the fluoride in drinking water and certain contaminants in known environmental waters, can be expressed using ppm or parts per million, ppb or parts per billion, or ppt parts per trillion, and many more. Now, what do we mean by ppm, ppb, ppt, and so on and so forth? These are basically ratio strengths, and they can also be represented as ratio strengths in weight, volume in volume, or weight in volume. But mostly, if the solute is a solid and the solution is a liquid, by default, the ppm or ppb or ppt are in weight in volume. So, 1 part per million means there is 1 part, usually in grams, of the solute per 1 million parts of the solution. The parts of the solution are expressed in milliliters. Now, let us illustrate how to interconvert these different expressions of concentration using the following exercises. So first, we are asked to determine how many grams of sulfuric acid will be used to make 1000 milliliters of 10% weight per volume sulfuric acid. So we will determine the amount in grams of sulfuric acid that will be required to make 1000 milliliters of 10% weight per volume sulfuric acid. So first, let us define that 10% weight in volume or weight per volume is the same as 10 grams of sulfuric acid for every 100 milliliters of the 10% sulfuric acid solution. Now, if we have 1000 milliliters of the solution, we can perform dimensional analysis to determine the weight of the sulfuric acid that will produce the 10% solution. So we will simply multiply the volume by the equivalent expression in ratio of the percentage weight in volume. So 1,000 times 10 divided by 100 will be equal to, we cancel these, 100 grams of sulfuric acid will be required to prepare 1,000 milliliters or 1 liter of 10% weight in volume sulfuric acid. Now, just like before, we can also perform ratio and proportion here. To determine the amount in grams of sulfuric acid that will be used to prepare 1,000 milliliter of the solution that has a concentration that is 10% or 10 grams for every 100 milliliter, then we can determine that the value of X is also equal to 100 grams. Now, if we have a concentrated acid, remember that um, these substances are corrosive substances and they are not often allowed to be weighed using analytical balances because these concentrated acids have capability to corrode the metal that is in your analytical balance. So most of the time, we need to instead determine the volume of the substance that we need to measure. We need to convert the weight of the sulfuric acid that we were able to determine to volume. Now, how do we do that? We need to take note that the sulfuric acid that will be used has this percent purity and this density. So, first, we will be using the percent purity. So, 100 grams of sulfuric acid will give you 10% weight in volume sulfuric acid in a liter or 1,000 milliliters of the solution. And now we know that we will be using a 98% weight of sulfuric acid. And that means that is a solution, a very concentrated solution of sulfuric acid with a weight of 98 grams of sulfuric acid for every 100 grams of the concentrated acid solution. So here we will be able to get the value of the concentrated acid that will contain 100 grams of the sulfuric acid. So cross multiplying, we get X equals 102.04 grams of the concentrated sulfuric acid. Now, this is still in grams. So we will be using the specific gravity to convert that into volume. So the volume is equal to 102.04 grams times the inverse of the specific gravity. Or simply, we will divide the specific gravity from this weight of the sulfuric acid. So volume is equal to 102.04 gram divided by 1.18. Remember the imaginary unit, grams per ml. So the volume is equal to 102.04 divided by 1.18. We get a value that is equal to 86.48 milliliters or about 86.5 milliliters of the concentrated sulfuric acid with a specific gravity of 1.18 and 98% weight in weight. Now, there is a shorter way to do this. Just remember the formula. Volume of the concentrated acid is equal to the weight of the acid divided by the percent purity expressed decimally. So we need to divide this by 100 times the specific gravity of the acid. So let's use this formula to determine the volume in milliliters of 100 grams of sulfuric acid. 100 grams divided by percent purity expressed decimally, so that's 0.98 times specific gravity, that is 1.18. So 100 divided by 0.98 divided by 1.18 is equal to the same 86.5 milliliters. So either way, you will get the same answer. Now, how about this problem, which involves percent weight in weight of sucrose content? What is the percent weight in weight sucrose content of syrup if it is made by mixing 850 grams of sucrose and 450 grams of distilled water? Now, take note that we are already given the weight of the solute and the weight of the solvent. So, the weight of the solution is simply the sum of the weight of the solute and the weight of the solvent. And then we will be using the weight of the solute and multiply this by 100 to get the percent weight in weight. And that will be equal to 65.4%. The weight of the combined water and sucrose is equal to 1,300 grams. How about these? We will need to convert the following expressions of concentration to percent weight in volume. Now, we have already showed how to convert this ratio 1 is to 25 to percent weight in volume, assuming that this is also a ratio that is in weight in volume. So 1 is to 25 is the same as 1 divided by 25. So we need to determine how many parts will be present of the solute will be present in 100 milliliters of the solution. So the x is equal to 4. So we say that the percentage weight in volume is equal to 4%. Now, for 1000 ppm, how do we convert this to percent weight in volume? Remember that ppm means parts per million. So, in this particular concentration, there are 1000 parts of the solute per 1 million parts of the solution. Now, we can convert this now to grams per milliliter. So we have 1,000 grams of the solute per 1 million milliliters. Next, we can use the formula for the percentage weight per volume, and that is 1,000 grams divided by 1 million milliliters times 100%, and our answer will be equal to 0.1%. Next, we have 10 milligrams percent. Now remember that by definition, 10 milligrams percent means it's 10 milligrams per 100 milliliters. So to be able to determine the percentage weight in volume equivalent of these, we simply need to convert this into grams. So 10 milligrams times the conversion factor, that is 1000 milligrams for every 1 gram. This is equal to zero point zero 0.01, because 10 milligrams are equivalent to zero point zero 0.01 gram. Then the percent weight in volume is equal to zero point zero 0.01 gram per 100 ml times 100. So it's the same as 0.01%. Now, how about these problems? If a solution contains 20% volume in volume of glycerol, how many milliliters of 20% volume in volume glycerol solution can be prepared from 1 pound of glycerol with a specific gravity that is 1.25? Now, in this particular example, we have an additional um, part of the solution which needs to convert 1 pound into grams. And because we are given the percentage strength of glycerol in terms of volume in volume, we will need to convert this mass unit into a volume unit using the specific gravity of glycerol. So remember that 1 pound is equivalent to 454.54 grams, or simply 454 grams. Now we know that the specific gravity of glycerol is 1.25. So we can determine the volume of glycerol from this formula: weight of the substance divided by the specific gravity. And this is equal to 363.64 milliliters. So this is the volume equivalent to 1 pound, or 454 grams of glycerol. Now, what is being asked is um, what will be the volume in milliliters of the solution that has a concentration of 20% by volume that can be prepared from this amount of the glycerol. So, meaning to say, this is the volume of the solute. Now, remember that 20% volume in volume is equal to 20 milliliters of the solute for every 100 milliliters of the solution. Now, we know that we have an available amount of glycerol that is equivalent to 363.64 milliliters. Now, we need to prepare 20% of the solution containing 20 milliliters of the solute for every 100 milliliters of the solution. So by getting the value of x, we will be able to determine the amount of the 20% by volume glycerol that can be prepared from 363.64 milliliters of glycerol, which is the same as 1 pound of it. That will be equal to 1,818.2 milliliters, or simply 1,820 milliliters of the 20% by volume glycerol solution. How about this problem? How many grams of a drug substance should be added to 240 milliliters of water to make a 4% weight in weight solution? Now, there are many ways for which you can compute the amount of the drug substance needed to um, be added to 250 milliliters of water to make 4% of the solution. So one is by using algebra. Now remember that the density of water is equal to 1 gram per ml. Therefore, 240 milliliters of water will have a weight that is equal to 240 grams of water. Now, the percent weight in weight is 4%. And that means there are 4 grams of the solute for every 100 grams of the solution. Now, we do not know the amount of the drug X that should be added to 240 grams of water to make 4% of the solution or 4 grams of solute present in 100 grams of the solution. So we express the amount of the drug as X. Now rearranging the the values in this equality, we have 100x. We will first drop the unit grams so that it will not be confusing. 100 x equals 4x plus 4 times 240, that will be equal to 960. Now putting this here, this will be 96x equals 960. So the value of x is equal to 960 divided by 96 or 10. We will put back the unit that is in grams. So you need 10 grams of the drug to be added to 240 milliliters of water to make a solution that um, has a percent weight in weight that is 4%. Now, there is another way for which you can compute this. Now, if the percentage of the solution based on the amount of the solute is 4%, then the rest of it, 96%, will be water. So 4% of the solution by weight is your solute or the drug, and the rest of it will be water. So 100% by weight minus 4% is equal to 96% by weight. And this is the amount of water that is present in your solution. Now we can use this value in a proportionality or in an equality where we know that in every 100 grams of the solution, we, we have 4 grams of the drug. And in every 100 grams of the solution, we have 96 grams of water. This is the same as 4% and 96%. Okay? So again, in every 100 grams of the solution, there are 4 grams of the drug. And in every 100 grams of the solution, there are 96 grams of water. It comes from these percentages. So to be able to determine the value of X or the amount of the drug, that will be added to 240 grams. Okay, so again, remember that the density of water is 1 gram per ml. So 240 milliliters of water will be equivalent to 240 grams. We can determine the value of X, which is also 10 grams. Now, our knowledge of expressions of concentration is not only limited to the pharmaceutical practice or in extemporaneous compounding and in manufacturing. In fact, our knowledge of expressions of concentration can be more applied in the laboratory. Different expressions of concentration are required to be used in the preparation of solutions which are needed in the quality control of substances. Now, in your laboratory, you may have already encountered some of these terminologies or abbreviations. According to the United States Pharmacopoeia, some of the reagents which are used in pharmaceutical laboratories are the following. We have test solutions or TS, colorimetric solutions or CS, and volumetric solutions or VS. Test solutions are intended for use in color reactions and as acid base indicators. Now, these are commonly used in tests where the change in the color of the test solution is observed to determine whether there is presence or absence of a particular compound in the substance or in the unknown solution. These test solutions are not normally standardized. Most test solutions are 10% weight in volume, but of course, there are exceptions. So you still need to consult the United States Pharmacopoeia whenever you prepare test solutions. For example, for acid base indicators, the concentration is often very low. Now, we also have the CS or the colorimetric solutions, and these are solutions used in the preparation of colorimetric standards for certain drugs and for the carbonization test with sulfuric acid. Some examples of colorimetric solutions are cobaltous chloride colorimetric solution, cupric sulfate colorimetric solution, and ferric chloride colorimetric solution. Now, what is common among these solutions are the fact no, that they are colored. We observe the intensity of their color in order to adjust the amount of certain drugs. So they are used as colorimetric standards. Now, in your quality control classes, you will also be preparing volumetric solutions. Now, when we say volumetric solutions, they may be normal solutions, molar solutions, or empirical solutions. Normal solutions are those solutions whose concentration are expressed in terms of normality. Molar solutions are those solutions whose concentrations are expressed in terms of molarity. And empirical solutions are solutions which are prepared um, from either of normal solutions or molar solutions. Whether made by direct solution or by dilution of a stronger solution, all these must be standardized against a primary standard or a solution with known concentration. You will be discussing these in greater detail in pharmaceutical analysis 1 or quality control. Just like what I mentioned before, whenever you prepare solutions, make sure that you use an appropriate glassware, such as the volumetric flask. The volume of the solvent that is placed in the or that is mixed with the solute is not always equal to the volume of the solution. Remember that even your solute will occupy its space. Now, you may use a graduated cylinder to approximate the amount of the solvent that you will need to dissolve your solute. Just, uh, just like what is shown here in this photo. So, you will put a small amount first of the solute, of the solvent to the solute, dissolve it, and then fill it to the mark. Now, if there will be a certain amount in the graduated cylinder that remains, do not use it because the volume measurement in a volumetric solution is more accurate. than the one that you read from the graduated cylinder. So, what do we mean by these expressions of concentration? So, first we have the molarity. The molarity is the number of moles per liter of the solution. The molality is the number of moles of the substance per kilogram of the solvent. Now, I have to point out something here. Remember that molarity and molality are almost the same in terms of their definition. They are ratios of the number of moles to the amount of either solution or the solvent. In molarity, we use liter of the solution, while in molality, we use kilogram of the solvent, not the solution. Now, normality is defined as the number of equivalents of substance per liter of solution. Now, you will be discussing normality in further detail in your other classes. So, we'll focus on molarity and molality this time. So, how do we determine the number of moles? Now, remember that the number of moles is basically equal to the weight of the substance in grams divided by its molecular weight, which is given in grams per mole. So notice that we can cancel out the grams and the answer will be in mole units. Therefore, molarity is equal to the weight of the substance in grams divided by its molecular weight divided by the volume in liter of the solution. Now, molality is equal to the weight of the substance or the solute divided by its molecular weight divided by its kilogram of the solvent. How about normality? How do we define number of equivalents? Number of equivalents is basically equal to the weight of the substance divided by equivalent weight. Now, in our later module, we will be discussing milli equivalents and milli equivalent weight. So we will just define this for now. So number of equivalents is equal to the weight of the substance in grams divided by its equivalent weight. Now, what is equivalent weight? Equivalent weight is equal to the molecular weight of the substance divided by its factor. Now, there's another question. What is the factor? Now, the factor differs depending on the substance that you have. For acids, the factor is basically the number of replaceable protons or H plus. For bases, the factor is basically the number of hydroxide ions that can be replaced in the substance. What do we mean by this? For example, we have hydrochloric acid, the factor will be 1. If we have sulfuric acid, the factor will be 2. For bases, let's say we have sodium hydroxide, its factor will be 1. If we have, let's say, magnesium hydroxide, its factor will be 2. Now, there are cases where the number of hydroxide ions is not obvious enough. For example, we have calcium oxide. Calcium oxide is actually a dehydrated form of calcium hydroxide, meaning to say, when you add water to it, calcium oxide will absorb water to form calcium hydroxide. And therefore, the factor for calcium oxide as well as for calcium hydroxide is equal to 2. Now, there are also cases where we have to deal with salts. Now, when it comes to salt, it depends on what is being asked. So we can either use the cation charge or the anionic charge, depending on what is being asked. Now, if we will take note of the definition of normality, which is the number of equivalents of the substance per liter of the solution, therefore, normality is equal to number of equivalents divided by the volume of the solution in liter. Number of equivalents is equivalent to the weight of the substance divided by its equivalent to weight, divided by volume, and then equivalent weight is equal to molecular weight divided by factor. So we divide this by volume. Now, dividing a number by a fraction would mean we will simply multiply it by its inverse. So we have this formula. Now, notice that weight over molecular weight over volume is basically molarity. So, normality is equal to molarity times factor. So just remember this formula, you are good to go when it comes to normality. Now let's take this problem as an example to determine the molar concentration of a solution. The solution contains 10 grams of cobalt 2 chloride dihydrate, whose formula is given here in enough ethanol to make exactly 500 milliliters of solution. What is the molar concentration of cobaltose chloride given its molecular weight? Remember that the molarity is equal to the weight of the substance, 10 grams, divided by its molecular weight, 165.87 grams per mole, divided by the volume of the solution in liters. Now, we are given 500 milliliters, and we know that 500 milliliters is basically equal to zero point 0.5 liter. So the molarity of this solution is equal to zero point 0.12 molar. How about this one? We have a solution that contains 90 grams of ammonium dichromate in enough water to give a final volume of exactly 250 milliliters. What is the molar concentration of ammonium dichromate given its molecular weight? Now let's do this step by step. Unlike in the previous item, we can compute for the number of moles, which is basically the weight, 90 grams, divided by its molecular weight, which is 252.07 grams per mole. The number of moles um, is equal to 0.3570 moles of ammonium dichromate. Now, the molarity of the solution is equal to the number of moles, 0.3570 moles, divided by the volume of the solution, which is 250 milliliters, but we need to convert it to liters, so that becomes 0.250 liter. And the molarity, therefore, is equal to 1.43 molar. Let's have further examples employing molarity and molality. Once again, we will not be having sample computation for the normality because we will further discuss equivalence, equivalent weight, milli equivalents, and milli equivalent weight later on in the final term. So first, how many grams of sulfuric acid are required to make 1 liter of 1 molar sulfuric acid? Now remember our formula. Molarity is equal to weight over molecular weight divided by the volume. Now, to be able to determine the weight, we will simply move the volume and the molecular weight to this side of the equality. So, Molarity times volume is basically equal to weight over molecular weight, or that is actually equal to the number of moles. Now we can move the molecular weight over here to determine the weight of the substance. So the weight of the sulfuric acid required to make 1 liter of 1 molar solution with a molecular weight of 98.079 gram per mole is actually equal to this 98.1 grams. So basically, this is equal to 1. So we just round this off to 98.1 gram of sulfuric acid. If you will recall earlier, we determined the volume of the sulfuric acid equivalent to this weight of sulfuric acid using its specific gravity. Let's say the specific gravity is 1.18 and its percentage purity is 98% by weight. So the volume is equal to 98.1 gram divided by the purity, which is expressed decimally, 0.98 times 1.18, the specific gravity of the sulfuric acid. This will be equal to about 85 or 84.83 milliliters. Now, we are asked to convert 10% weight in volume sulfuric acid to moles per liter, given that the molecular weight is 98.079 gram per mole. Now, let's try to use dimensional analysis in calculating or in converting 10% weight in volume to molarity or moles per liter. So 10 grams per 100 milliliters um, is an expression that is equivalent to 10% weight in volume. Now we have grams here. So what we can do is we can cancel that out using the molecular weight of the sulfuric acid. We cancel the grams. Next, we need to convert the milliliters to liter because according to the definition of molarity, it is moles per liter. 1,000 milliliters are equivalent to 1 liter. So we cancel the milliliters. We are left with moles per liter. So 10 times 1,000 divided by 100 divided by 98.079, this will be equal to approximately 1.0 molar. Now notice that 10% weight in volume sulfuric acid is approximately equal to 1 molar sulfuric acid. In the previous slide, we determined that to be able to prepare 1 liter of 1 molar sulfuric acid, we need to have 85 milliliters of the concentrated acid. Recall that in the previous section, we also determined the amount in weight and in volume of sulfuric acid required to make 1 liter of 10% weight in volume solution. And it's the same. How about molality? Remember our definition for molality. Molality is equal to the number of moles of the substance per kilogram of the solvent. So it is important that it's the kilograms of solvent. Now, unlike your molarity, molality has a unit that is a small letter m. So first, we can determine the number of moles of the solute, which is sucrose. And because there are 850 grams of sucrose in the solution, we divide this by its molecular weight. 342.2965 grams per mole, and this will be equal to approximately 2.5 moles. So molality is equal to 2.5 moles divided by the number of kilograms of solvent. Our solvent is distilled water, and we need to convert 450 grams to kilograms. So that will be 0.45 kilogram. So this will be equal to 5.5 molal. Of course, we can also use dimensional analysis to be able to calculate the molality of the solution. So we begin with your the weight of the sucrose, 850 grams. We multiply to it the inverse of the molecular weight. 1 mole of sucrose weighs 342.2965 grams. Next is we divide from it the weight of the solvent used, which is distilled water. So we just need to multiply it by the inverse of the weight of the solvent and convert that weight into kilograms. So we also get the same answer, 5.5 molal. Now remember that previously we also computed for the percentage weight in weight of the sucrose in syrup and F, and it was determined by this formula. Okay, so that means that for syrup and F, it contains 65.4% weight in weight of sucrose, and its concentration of sucrose is equivalent to 5.5 molal. That ends our discussion of methods of expressing concentrations.